This will be the first of a few computer architecture lessons. One resource I find that's extremely useful is this PDF that you can download by Googling it. It's a synthesis lecture on computer architecture by these guys. And it's quite the good tool because it's only 116 pages, but it's like 116 short pages. And most of it is like, like just like the abstract and table of contents. It's like already 11 pages. Um, it's I find this useful because it's a very short and concise and condensed refresher on everything from basic to more advanced concepts of computer architecture. So if you're doing like hardware interview, as you know, hardware interview is like if if software interviews were a lot harder. It's terrible. And then so basically you have to do Verilog coding questions, but they can also ask you everything about computer architecture and physics trade-off and things of that nature, all the way to your CMOS or PMOS or whatever, to drawing gate diagrams, to drawing digital logic and converting back to Verilog, talking about timing, power, area trade-off. It's like everything from the first principles physics that they can ask you all the way to the most abstract um, Verilog implementation of, let's say, a find first uh, thing, right? So we're going to start in the sort of middle here in kind of a crux of computer architecture, especially if you're looking to work for companies that developed, high performance chips. For me, computer architecture is like for one of the roles that I'm applying to. So this will just have some brief study, but it's still somewhat of a study that is sort of required. And if this doesn't really take that long to run through, compared to like actually practicing code, so just kind of remembering, getting a refresher, memorizing this will be good. In the future lectures, I might actually draw some stuff out if it's actually difficult. But for the most part, I will just kind of read, like for the introduction, I won't draw anything because the introduction touches like everything else in a very high and abstract level. So I'll just run through the introduction in this video, and then in future videos, if I feel like I need to draw something, namely if the diagrams in this PDF isn't sufficient, I might go into more detail. So consider, I guess, this series a very condensed version of like a university plus computer architecture course with the prerequisites that what like logic gates are and things like that. Anyway, in the introduction, I read this yesterday, so I'll just kind of summarize it. The introduction kind of doesn't matter for these opening paragraphs. Yeah, it's just saying like there's different types of computers, and then they're talking about definitions of architecture, so pipelined and non-pipelined. You don't really need to know non-pipeline processors because they don't really, like, no one's going to ask you that in digital logic design space. Yeah, practically used by all processors nowadays, so it's just pipeline, right? Pipelining, for those that don't know, which should be a pretty big concern. If you're in the industry and looking for a more senior position, is pipeline is just basically you use flops to store information so that you can jack up your CPU frequency and to instruction level parallelism, increasing that higher throughput, so on and so forth. In order processors, and again, if this is more of a refresher and not a brand new thing, right? You would know that in order processors only process things strictly in order, but that's extraordinarily slow compared to other order processors where you can execute future instructions by predicting a branch or just like like executing future instructions that's not necessarily committed yet. So basically speculative machine. Scalar and superscalar. So I guess, yeah, a scalar processor is one instruction per cycle for any code. Superscalar is you can have multiple instructions per cycle. So IPC is more than one, can be superscalar. So for example, if you have multiple reservation stations and you're kind of executing a bunch of ops in parallel in one cycle and like multiple different pipelines, then um, you're superscalar, right? Okay. I guess does this also imply you're retiring multiple instructions per cycle? Or just the execution of? Okay, it looks like the opening paragraph just doesn't talk about retirement. It's more like execution. But I guess that's semantics. Like you could have a reorder buffer that retires more than one instruction per cycle. Um, though I would say that's probably not the bottleneck. Yeah. Yeah, so vector processors, if you're familiar with SIMD instructions, so SIMD instructions is like, let's say you have 32 bytes, but then you can divide the 32 bytes into 4 individual byte lanes. So byte 0, byte 1, byte 2, byte 3. And then each of those can represent those 4 separate bytes. Yeah. So let's say you have 4 byte instruction and each of them are split, like each of the bytes are split into its own lane. And in each own lane, it's, let's say its own operation. So for example, you have like 4 bytes plus 4 bytes. But you can, instead of treating the 4 bytes plus 4 bytes as like A plus B equals C, you can say, well, I want the byte 0 of A plus the byte 0 of B to give me the sum and then return it in the destination register in the byte 0 of C. And then byte 1 of A plus byte 1 of 2 will be returned in the register of byte 1 of C, and so on and so forth. All right, so this basically crams a bunch of parallel operations into a single op. So instead of having the machine issue like 4 adds in my example, you can just have one instruction and it'll execute 4 adds. And so then the trade-off is your adds are not as wide, right? In this particular case, you're kind of limited to a single byte for your answer. So I guess vector processors are just like, you can have like very, very long vectors, right? Like you can theoretically build a machine where you can execute instructions that's like thousands of bytes, and then all of them are kind of just split into kind of like 32 bytes, and then you can execute, a lot of 32 byte adds in one op in a 1024 byte wide bus. Okay. Multi-core processor just means there's multiple cores in the processors. Multiple thread processor just means that a single processor can have simultaneous multi-threading. So you could have one CPU, and then the CPU could just be architectured in such a way that you can have multiple threads, and it can round robin or whatever arbitration scheme is between them to switch between the threads. And then I think they note that both of them can execute multiple threads simultaneously, and yeah, and then you can have multi-core and multiple thread be combined, right? Obviously, so you have 4 cores, each core being able to execute 2 threads, and then so 4 times 2, it's 8 maximum threads you can execute. All right, market segments, you could maybe just skim this because servers are just servers for websites. Desktop, you know what that is. You have a phone, so you know what that is. These are like, I don't really know what this is. Embedded. Embedded is like kind of like custom ASICs, I guess. But if you're in digital logic design, yeah, I mean, I guess I could see that. I just haven't really designed any like hospital equipment. It's more like CPUs and stuff like that. Overview of processor. Um, okay, yeah. So let's just go to the diagram then. It's just saying that you have an iCache, and the iCache, I guess, can also get things from L2, L3, TLB, with the virtual address to physical address lookup, which we're going to go through later. Basically, this iCache says and stores all the instructions to be executed by CPU in a cache, and then this fetch stage, it's not one pipe stage, but this like phase of the machine is just going to go ahead and deal with all the memory requirements of being able to grab all the instructions you want to execute and shove it in the cache, and then reading it and then hitting it in the cache and then passing it to the decode phase. The decode phase will take these x86 or ARM instructions, and then it'll generate a bunch of control signals and a bunch of metadata, I guess breadcrumbs for the instructions to be processed down the line. So then once it kind of generates all those signals, that payload will be passed to a rename phase. The rename phase will say, well, what's the source registers, destination registers, and then deal with any false dependencies, right? If you recall, like raw hazard, wall hazard, or hazard, read after write, write after write. It's gonna just basically detect those things and then just rename the registers in such a way that I believe using like the map table and stuff, which we'll kind of go over later, then you're going to have like architectural registers. While those might be repeated and non-unique, you're going to translate them to, or are they called logical registers? Basically, the software registers, the software sees might be not unique, but then the hardware registers that's internal to the CPU is going to uniquify them, given that the dependencies are false and not real, right? Obviously, if the dependencies are real, then then you actually need to wait for the result to come back, i.e. a read after write kind of thing, right? So anyway, you do this renaming scheme, so then all the internal register names are correct and you won't have any false dependencies, so you can maximize performance. And then that payload will be now, because keep in mind, we don't want to do anything that's with software register name, but like the internal hardware register name, right? So a lot of payload will go to the issue queue, so the issue queue can know what to wait for, what not to wait for, and if an operand is ready to be executed. So the issue queue is just a queue, and then it's just going to wait for the proper conditions. And when the conditions arrive, probably with the help of scheduler, it's going to issue those instructions to be executed. Executed will go to ALU or some other like execution pipeline, and then it'll go ahead and when the results come back, it'll write the registers, and it'll also read the registers. Like if A plus B equals C is what you're trying to execute, then it needs to read source A and source B from this physical registers file. And then as you go into the issue queue, then there's some metadata breadcrumbs you need to put in the reorder buffer, because those are the things that need to be executed, and the reorder buffer will keep program order coherent. So there's kind of some in-orderness that's kind of embedded in this kind of dispatch into the reorder buffer. And then there's also like if you have agents or address generation to know what address to load to store from, it'll also go to load store queue, right? So load store queue execute loads and store in memory operations. That's going to change the actual memory and state of the computer, and those get executed here, whereas the issue queue can just be like add, fmac, imac, multiply, accumulate, subtract, multiply, whatever. Those instructions in the computer, that doesn't absolutely necessarily have to go into memory, right? Whereas LSQ, you're actually saying like store this register into memory at this address or something like that. Okay, so LSQ is going to communicate with the data cache, right? Just as the iCache has the instructions, data cache will have data. And then data cache also can update the physical register files, right? Because if you're pulling some thing in memory and you need to load it to a register, so that if an instruction requires one of the source from memory, then that's what you need to do. And then so once you're done executing the instruction, you can finally write it back into the register file, or again, if this is just like an agen or address generation, then you write back the destination address in the load store queue, for example, so you know what address to load or store that particular instruction. And then once everything's done, then you go to this commit phase, and the commit phase is just going to be essentially a phase that's committed to, pun intended, updating the architectural state so that it's permanent, right? So there's anything happening like with branch mispredictions or some exception or things like that, the reorder buffer will then know like, all right, this branch prediction or this exception happened in entry n. We're currently at entry n plus k, so then there needs to be k entries that needs to be rewinded or flashed architecturally back so we can restore the old architectural state. So we can start over from the branch prediction or the exception. Whereas if you commit it, it's done, right? It's like permanently done in the system. It's kind of like if you finish a blockchain transaction or something like that. It's permanent, and like this is past any sort of exception, right? So yeah, so that describes a lot of that. Okay, this is saying what I described in the diagram. And then so I guess chapter 2 is the caches, which I'm probably going to read and then I'll summarize in a different video. But I think the introduction kind of hits like super duper condensed high level of how a computer works. So if it's a pure refresher for you, that should be at least enough to get like an engine going. But then I think like caches is more deep dive, right? Like if you remember college courses, like as an example, like your index, your byte offset, your n-way associative stuff, all that good nitty gritty detail will be covered in the rest of the pages here, which will be reviewed in future videos.